All right, it is 9:20, so let's get started. Good morning. For those of you who are taking the class at UCSC, congratulations. You just finished 20% of the course. Only 80% left to go. So, last time we started to talk about causal broadcast, and we started to sketch out an implementation of causal broadcast using vector clocks. And we didn't really write down the rules in any kind of a formal way. So this time we're going to start out by doing that. So let's come back to this topic of causal broadcast. And just to refresh our memory from last time, let's put up our picture again of our classic causal anomaly. So what we figured out last time is that the issue here was that this message here was delivered before this message being sent by Alice, even though this message should be causally later. And we sketched out how we could use vector clocks to prevent that. In particular, if every process is keeping a vector clock, and then these messages have vector clocks attached to them when they're sent. So for example, this first message from Alice, its vector clock is 100. So it's incremented in Alice's position because this send on Alice counts as an event. The message arrives at Bob, and Bob is okay to deliver it because it's only bigger than Bob's in one position. It's bigger than Bob's in the position of the sender. So Bob is okay to deliver that message. When this message gets sent, the vector clock attached to it is 110. Because Bob now knows about the one event from Alice and he's now incrementing one for this event on himself. Again, we're only counting message sends as events. So receives don't count as events in this particular algorithm. This message arrives here, but then it gets queued because a message with a vector clock of 110 at this point on Carol is too big to deliver. So this message gets queued. This other message arrives with its vector clock of 100, and that one can be delivered. And at that point, this message can come out of the queue and be delivered. This one over here could be delivered right away. So that's one example, but what are the rules in general for doing this? So let's start to write that down. Okay, so causal broadcast. So first rule, if a message sent by process 1 is delivered at process 2, increment process 2's local clock in the process 1 position. So maybe we should have done that here just to make it a little bit more explicit. So here, this message is being delivered at Bob. Because the message was coming from Alice and it's being delivered at Bob, we should increment Bob's local clock in the Alice position. So that should change to 1 there. Here, nothing changes according to that rule because this message just gets queued. Here, this one, Alice, this would have already changed to 1, and then this would change to 1. And then finally here, we can update Alice's clock when this message gets delivered, and then when this one gets delivered as well. So that's the first rule. Then we say, if a message is sent by a process, first, increment its own position in its local clock and include the local clock along with the message. So these vector clocks are being attached to these messages as metadata that comes along with them. All right, last one, the tricky one. This is the property that tells you when it is that you're allowed to deliver a message. So we say, a message sent by a process P1 is only delivered at P2 if, and we're going to say this message sent by P1 has a timestamp, which a vector clock. So if for the message's timestamp T, and this is a logical timestamp, so this is not like a time of day timestamp, it's a vector clock. This condition has to be true. I'm kind of running out of room, so I'm actually going to move to another sheet here. We say that the timestamp, and this again is the vector clock attached to P1, or excuse me, the vector clock attached to the message coming from P1. So in the P1 position on that vector clock, it has to be the case that the vector clock on the process that we're sending to that one has to be one less. So the timestamp of P1 in the position of the process that we're sending from has to be one bigger than whatever that position was in the vector clock on the receiving process. So that has to be true. And it also has to be the case that the timestamp for every other position, let's call it K, has to be less than or equal to that position in the vector clock on the receiving process. For all K other than the K of the process that's sending the message. So I'm going to write down condition 3 up here again. So these are the rules. Rule for when you can deliver a message sent from P1 at P2 under causal broadcast. So what do these two conditions mean? So the first one up here means that the timestamp on the message makes it the next expected message from P1. That's what this condition says. So T is the timestamp of the message coming over from process 1. VC here is whatever the process 2's local clock says. So this condition says that, for example, if the message comes from Alice and it has a timestamp of 100 and Bob's local clock is 000, then that's okay, because in that position, in Alice's position, it was one higher. Then there's the other condition here, which says that for every other position in the vector clock other than the sender's position, the timestamp is at most as big as the local clock. In other words, it says that there are no messages missing from any other processes out there. So that's what these two conditions ensure. The general idea here is to make sure that the sender doesn't have more information than the receiver about the state of all of the other processes. So in particular, we want to rule out this kind of situation where where this message here would cause confusion on Carol because Carol knows about some state, or because Bob knows about some state that Carol doesn't know about yet. So this rule is what makes it possible for us to queue this message here rather than delivering it immediately. Here's that rule again. Questions about this? So there's a question in chat which says, with these rules, wouldn't Bob's clock be 200 after delivering the first message from Alice? Well, let's look at it. So after delivering the first message from Alice, so like right here, I'm not sure why it would be. So Alice, at this point, when she sends this message, it has a timestamp of 100. I think what you're thinking of is that I think you're still thinking of the notion of counting receives as events. So yeah, so keep in mind that with this particular algorithm, we don't count receiving of messages as events. With the vector clock algorithm that I showed before, when we were just assigning vector clocks to events and we were using that to determine which events happened before other events and which events were independent, everything counted as an event then. Receives counted, sends counted, internal events counted. But with this, we only count sends as events. So there's another question in chat. So when the local clock is sent by a process, we don't absorb the local clock into the new process, or we don't absorb the sent clock into the new process. No, we absolutely do. So when this message from Alice arrives here at Bob, right? Bob's clock here increments here in the Alice position because that message came from Alice with a 1 in that position. So yeah, we're still definitely using the clocks that are sent along. Otherwise, we wouldn't need to send the clock as metadata. But we still need to use that information. So we say, if a message sent by process 1 is delivered at process 2, that's when we increment process 2's local clock. So this is where the increment occurs. So it happens at delivery time. So this is the complete algorithm. I've written down everything here. There's not some implicit information about taking the maximum of vector clocks. This is it. So so the question in chat is confusion about when to do step 1. Maybe you're assuming that there is some taking the max of vector clocks that happens externally to this algorithm, but this is actually it. So this kind of I forget the word I'm looking for here, but this subsumes, that's the word I want. This subsumes what we were doing before with taking the maximum of vector clocks, if that makes sense. Yes, so that's why, so the question in chat now is, are all messages always sent to all processes? Yeah, so that's why it's causal broadcast. So this would not work if we weren't sending all messages to all processes. So that's a great question. So I think somebody asked this actually last time. So the question last time was something like, oh, well, what if Alice only sent her message to Bob and then Bob sent his message to Alice and Carol? Then would this message be delayed? So there was a question like that. And I think I kind of made light of the question last time and said something about how that would make Bob a jerk, which it would, but also that wouldn't make sense under this algorithm, because in this algorithm we're assuming that all messages are broadcast messages. So a message that just went from Alice to Bob, this technique for ensuring causal message delivery wouldn't work then, because this is only for when all messages are broadcast messages. Now it turns out that a lot of the time that's what you want. So this is a very useful algorithm. If you wanted to ensure that all messages were delivered, if you wanted to ensure causal delivery in a setting where not all messages were broadcast messages, that's something that you can think about on your own. You'd have to do something a little bit more sophisticated then. So I think there's a little bit of confusion in chat about this versus what I showed earlier. So these are both algorithms that use vector clocks. And before, what we did was, when you received before we were talking about using vector clocks to assign, or we were talking about assigning vector clocks to events that had already happened. So we were saying, looking at a collection of events that have already occurred, let's assign vector clocks to those events so that we can try to understand what happened before what. This is a little different because we're talking about, as the events are occurring, we're talking about using vector clocks to decide whether or not to deliver messages as they're happening. So these are, it's the same concept in either case, but they're different uses of vector clocks. Yeah, so another question is, after we've completed all the sends, are all the vector clocks for each process 110? Yeah, that's right. So this one here for Bob should have been 110. Or rather, not after we've completed all the sends, but after we've completed all the delivers. So let's do another example. I'm a little bit bored of this one. So let's say again, we have Alice, Bob, and Carol. Okay, so say Alice sends a message here, and she says, I lost my wallet. And let's say she sends that to Bob and Carol. And the vector clock attached to this message is 100. Is this message okay to deliver when it gets to Bob? Sure. So it gets delivered at Bob. It's also okay to deliver at Carol. Alice sends another message. Say she finds her wallet. To Bob. Is this one okay to deliver? Yeah, you bet. So this one gets delivered too. Bob sends a response. Glad to hear it. Maybe you see where this is going. Oh yeah, this should have been broadcast. It is broadcast, but we're going to say that this one takes a little bit longer. So maybe now you really see where this is going. So Bob says, glad to hear it. Sends that to Alice. I suppose I should write the vector clock here too. So this was 200. What's the vector clock attached to this glad to hear it message? Yeah, that's right. That one should be 210. It gets here. Is it okay to deliver that message at Alice? Sure. Deliver that one. But if it also comes over here to Carol, is that one okay to deliver? Nope. Thankfully not, right? Because Carol would probably be pretty unhappy if Bob's response to Alice with losing her wallet was, glad to hear it. So that one gets queued. And then finally this one arrives. So this message here had 100. So Carol's local clock has now been incremented to 100. When the next message arrives from Alice with the clock of 200, that one's okay to deliver too. So that one can get delivered. And then finally, so this 200 corresponds to both this and this here. And then finally, this one down here that got queued is okay to deliver now. So here, again, the causal broadcast algorithm prevented some horrible faux pas from taking place. So Carol does not see this glad to hear it message until she sees Alice's message saying that she found her wallet. So there's a question in chat. Don't we have a problem when two processes send at the same time and messages pass each other? So this is a great question. Yeah, so this actually anticipates the next thing that I want to talk about. So the next question is, does this vector clock stuff establish a total order on messages. Remember what our total order anomaly looked like. So what if we tried to prevent this total order anomaly using vector clocks? What would happen? Well, okay, so we got client 1 here, right? Sending a message. So what would the vector clock on that message be? 1, 0, 0, 0, right? Message arrives at replica 1. It's okay to deliver. Client 2 is sending a message here, so the vector clock on this one would be like 0, 0, 0, 1. Message arrives at replica 2. If these processes all start out with 0, 0, 0, 0 as their vector clocks, then this one's okay to deliver, right? Because it's only one bigger than replica 2's local clock in the sender's position. So we go ahead and deliver it. This one arrives here. So now at this point, replica 1's local clock looks like this. The message from C2 arrives. Replica 1's clock is 1000. The message from C2 is 0001. Is that okay to deliver according to the rules that we had before? So here's the rules. So we said the timestamp on the message from the process that's delivering it has to make it the next expected message. So it has to be one bigger in the position that it. So this is the vector clock. This T here is the vector clock on the incoming message that's attached as metadata to the message. So this has to say it's one bigger than whatever the local clock on the process receiving the message thinks for that particular, for that sending process's position. But then here, we say the timestamp for every other, on the vector clock attached to the message, it has to be less than or equal to the vector clock on the receiving process for every position. So is that true here? Well, yeah, it is. So this vector clock attached to the message 0001, it's one less than this clock up here, but that's okay because this is less than or equal here. So that's actually fine. The point of this rule is to rule out messages that are coming from the future. But this message isn't coming from the future. Replica 1 receives the message with this timestamp of 0001. The only place where it's bigger is in the sender's position, and it's only bigger there by 1. So according to the causal broadcast algorithm, this is actually perfectly fine to deliver right here. Likewise, here on replica 2, so right now replica 2's clock is 0000, or it's, yeah, 0001. This message comes in. It has a timestamp of 1000. It's one bigger than the current clock in the sender's position, that first position there. It's less than the sender, it's less than the receiver's clock in this last position, but that's okay according to causal broadcast. So this one's actually okay to deliver too. So these messages here, the ones that could potentially cause these replicas to disagree are actually fine to deliver under the causal broadcast algorithm. So, causal delivery doesn't rule out total order anomalies. And we kind of saw that hinted at before, didn't we? Because when we sketched out a hierarchy of delivery guarantees, we saw that total order was on its own branch, right? We saw that it wasn't it wasn't a more restrictive delivery guarantee than causal delivery, and so nor was causal delivery more restrictive than it. So there are some things that are total order anomalies that ensuring causal delivery still wouldn't rule out, and there are things that are causal anomalies that ensuring total order doesn't rule out. So no, we can see that these messages here are not in violation of the causal delivery protocol that we wrote down. So if we wanted to enforce total order, if we wanted to rule out anomalies like this one, we would need something more than vector clocks. Or at least if we wanted to keep causal order and also have total order, we would need something more than this particular causal broadcast algorithm that we just wrote down. In general, total order is really annoying to have to enforce. So I suggest not enforcing it unless you really have to. Questions about this? All right. So I want to pause and do a quiz question. But I also want to talk about the answers to the quiz questions from before. So here were our quiz questions from last week. So on Monday of last week, we asked about if A happens before B, then what can you say about the Lamport clocks of A and B? So this is what you do know from Lamport clocks, right? If A happens before B, then we know that the Lamport clock of A is less than Lamport clock of B. We don't have the other direction with Lamport clocks. We only have this direction of that implication. So in particular, if the Lamport clock of A is less than the Lamport clock of B, you don't know that A happened before B. It could be the case that A and B are concurrent, or it could be that B happened before A. That was from Monday. On Wednesday, we asked about vector clocks, pointwise maximum. So this is pretty straightforward. You just take these two vector clocks and you take the max in each position. So if the clocks are 0, 2, 1, 0 and 0, 1, 0, 3, then the pointwise maximum in this case is going to be 0, 2, 1, 3. And then Friday, we said, complete the definition of the Fifo delivery process. We said if a process sends message M2 after message M1, and the answer here is if a process sends M2 after M1, then any process that's delivering both of those messages, and we're talking about the same receiving process, any process that delivers both of them messages has to deliver M1 first. That's Fifo delivery. So those were our quiz questions from last time. And now let's do today's quiz question. So I'll post it in chat. Yeah, I'll fix it. Okay, should be fixed now. All right, we'll wait like 1 more minute. Okay, let's call it good. Okay. Back to the lecture. So, so we've just been talking about causal broadcast, right? And I want to say something about ways that potential causality and by potential causality I mean the happens before relation is used in distributed systems. So we just talked about 2 of them, right? We talked about how we can use vector clocks to assign. We can assign vector clocks to events to determine the ordering of events after the fact for debugging. And then we can also use vector clocks or this notion of happens before live while an algorithm is running to do things like causal broadcast. So I'll just say causal ordering of events as they're happening. So sometimes you'll hear people talk about causal consistency. Is not quite a synonym with causal broadcast, but they're related. So all these things provide ordering guarantees that prevent causal anomalies. What's something else that you can do with causality? So one thing that we haven't talked about yet this is kind of related to the first point, is what's called consistent global snapshots. So this is a way of getting a picture of the global state of a distributed system. And it's not trivial to do because each of these processes in a distributed system has its own state, right? And its own knowledge about other processes' states. So there are some ways to try to take a global snapshot that makes sense and some ways that really don't make sense. But as a general rule, it may not surprise you to learn that if A happens before B and B is in the snapshot, then A should be too. So this notion of consistent global snapshots is another important use of the happens before relation, or another important use of potential causality. And that's what we're going to talk about next. So before we get into the details of this snapshot algorithm, let me just kind of talk at a high level about what it means to try to take a global snapshot of a distributed system. So something that we've talked about a little bit so far is that in a distributed system, there's not really such a thing as an observable global state, right? So individual processes have states, and we said that the state of a process, right, amounts to all of the events that have taken place on it, right? So if you have a bunch of events, maybe these ones are internal events, and then maybe there's also some messages being received, maybe there's some messages being sent, and so on. So we say that a state of a process amounts to all the events that have happened on it up until some particular point. And we could also say that whatever it's storing in its local memory could be part of that state, but that could also be expressed as internal events. In any case, I could sort of lasso up all the events that have occurred on a process and then say, ta-da, there's its state. But in general, we have several processes, right? And we want to be able to talk about the state of the entire system. So if we had some sort of globally synchronized time of day clock, we could say, okay, everybody take a snapshot of yourself at 9:20 a.m. But we can't do that because my 9:20 a.m. isn't necessarily the same as your 9:20 a.m. So this could lead to problems. So just to give you an example of that, for instance, what if, let's say one process's clock, let's say P1's clock, is set a little bit earlier than process 2's clock. Then process 1 might take a snapshot at what it thinks is 9:20 a.m. and then it might send a message to process 2. So let's say that some events have happened on process 2, and let's say that right here is what process 1 thinks is 9:20 a.m. So it takes its snapshot there. Let's say it sends a message right here. And let's say that this is what process 2 thinks is 9:20 a.m. So if process 2's clock ticks over to 9:20 a.m. after receiving that message, and maybe some other events happened on process 2 before this, then the snapshot on process 1 would look like that, but the snapshot on process 2 would look like this. So then we would have a snapshot that didn't make sense, right? Because we would have this event here that was supposed to happen before this event, according to the happens before relation, because it was the send that goes with this receive, but it's not in the snapshot. So we have this event that's in the snapshot that came from nowhere because we tried to use time of day clocks. So this approach of telling everybody, okay, take a snapshot of yourself at a particular time, this is prone to errors because not everybody's clock can be perfectly synchronized. P2's piece of the snapshot here says that it got a message before 9:20, and P1 says it never happened. So clearly time of day clocks are not going to be good enough for us in taking snapshots. So what we need is some sort of algorithm that will allow us to take a global snapshot that actually makes sense. So we're going to start to talk about a classic algorithm for doing that. And it's called the Chandy-Lamport algorithm. As so often in distributed systems, it's named after Leslie Lamport. And also somebody else, Mani Chandy, another famous distributed systems person. So the story behind this is that, so supposedly they were hanging out over dinner one night and talking about how to compute distributed global snapshots. And according to Lamport's version of the story, they'd had a little too much wine and they couldn't figure out how to solve the problem right then. So supposedly, according to Lamport, he came up with the solution in the shower the next morning. And he went to Chandy's office, and Chandy was waiting for him there with the same solution. So they ended up co-authoring this paper about it. So let's talk about how it works. It's actually fairly straightforward, I think. So first, I'll try to write down what the algorithm does, and then we'll work out an example together. Actually, I don't know if we're really going to have time to write down what the algorithm does today. We might have to save it till next time. So first I'm going to establish some terminology, and then we'll see how we do. So the new piece of terminology that we need, that I kind of hinted at a little bit before when we were talking about Fifo, is the notion of a channel. So a channel can be thought of as a connection from one process to another. So let's say if we have processes P1 and P2 that are sending and receiving messages. There are actually two channels here. There's a channel from P1 to P2, and there's a channel from P2 to P1. So the convention in naming these channels is the channel from P1 to P2 is called C12. And the channel from P2 to P1 is called C21. So in general, channel Cij is the channel from process Pi to process Pj. So in this picture, one message has been sent from process 1 to process 2. So at this point, we're going to say this message has already been sent, the one that where the send is event A and the receive is event B. And then there's this other message here whose send is event C here. And this message is currently in flight from P2 to P1. So we say that this message from P2 to P1 is currently in the channel C21. So in this particular picture, channel C12 is empty because there's no messages currently in flight from P1 to P2, and channel C21 has one message in it, this message right here. We're going to assume that messages arrive in Fifo order. So that is, there's no Fifo violations. So channels will act like Fifo queues. So this is enough to prevent Fifo violations. As we've seen, preventing Fifo violations is not enough to prevent violations of causality, and it's not enough to prevent total order violations. But at least we have this. So we're assuming that messages only get sent in Fifo order. Okay. So let's, in the short time that we have left, let's try to do a really simple example of running the Chandy-Lamport algorithm. So one particular process kicks things off, and we call it the initiator process. So say again that we just have P1 and P2, and we have a message like this, and then one like this. Let's say that P1 here is the initiator process. Let's say that P1 decides to start taking a snapshot, and it takes that snapshot right after message A is sent. So what it does is it records its state right there. We're going to call this S1. After it records its state, it sends what's called a marker message. And it sends that marker message out on all of its outgoing channels. In this case, it only has one outgoing channel because there are only two processes in the system. So it has its outgoing channel to P2. So it sends what's called a marker message. And I'm going to draw this differently to differentiate it from these ones up here, these are messages that are actually part of the running application. So this one is a marker. It sends a marker message. It has to do that before so it does that. I really should have drawn it starting up here. It has to do that before it does anything else after snapshotting its own state. And then, after it sends that marker message, it starts recording the messages that it receives on all of its incoming channels. In this case, it only has one incoming channel, the one from P2. Okay, so what happens when somebody receives a marker message? There are two cases. So when a process receives a marker message, if it's the first marker that that process has seen, it records its state. It marks the channel that it got the marker message on as empty, and it sends a marker out on all of its outgoing channels. If it's already seen a marker message before, then it's going to stop recording on that channel, and it's going to set that channel's final state as all of the incoming messages that arrived since recording began. So TLDR, if it's already seen a marker message and it receives another one, then it stops recording incoming messages on that channel. That's a lot of words, so let me try to summarize it in this picture a little bit better. So in our example, P2 records its state right here when it receives this marker message. I'll call this one S2. It doesn't have any other incoming channels to record on, right? So it doesn't have to do that. And what it does now is it sends a marker message back to P1. And it marks its incoming channel as empty. What does P1 do when it gets the marker message? Has it already seen a marker message? We say that it has. It sent one in the first place. So that we say that counts as seeing one. So yes, it saw one. So what does it do? It stops recording on its incoming channel that the marker message came in on. Did it record anything during that time that since it sent its marker message? Let's say that it did. Let's say that this message actually arrived over here. It got this message whose send was C and whose receive was D. So that actually has to be captured somehow. So that actually goes into the recorded state. So now we have everything recorded. We have the state of process 1, we have the state of process 2, and we got the state of the channels. So this snapshot is done. Does this snapshot make sense? Well, what would be a snapshot that didn't make sense? So it would be really, really weird, right, if the snapshot had B but not A, right? So this would be, here's a snapshot that wouldn't make sense. So if this were S2 and this were S1 over here. So this would be a snapshot that wouldn't make sense, right? Because we have this A here, and then we have this B that's supposed to, A is supposed to happen before B, but A wasn't captured as part of the snapshot. Or here's another one that wouldn't make sense. This one wouldn't make sense either, because we've got C here, but we don't have B, which happened before C. So these would be weird snapshots. As it turns out, the Chandy-Lamport algorithm won't let you take a snapshot like that. What if it's something like this? So is this one a legal snapshot? Yeah, this one's a perfectly good snapshot. So what happened in this case is process 1 snapshotted its own state. It sent a marker message. And then say the marker message, responding marker message from process 2 came back pretty quickly. So this message from C to D never gets, neither of these events ever gets included in the snapshot. But it turns out that that's fine in terms of it being a legal snapshot. And what happens is that all of these individual snapshots of the different processes get stitched together by the Chandy-Lamport algorithm into the global snapshot. Or really, I guess I shouldn't say that doesn't happen as part of the Chandy-Lamport algorithm. The algorithm is done running at the point when every process has snapshotted its own state. And then you could imagine some other process running later that goes around and collects up all of the individual snapshots of the individual states and stitches them together into a global snapshot. So I went through that really quickly because we only had a few minutes, but just to talk about some big picture stuff. So these marker messages are messages that get sent as part of the snapshot algorithm itself. So the marker messages don't themselves get included in the snapshots that we're taking, because what we want to do is take a picture of the state of the system, and we don't want the snapshot algorithm itself to interfere with the snapshot that we're taking. So the marker messages are just an artifact of the snapshot algorithm. You wouldn't want your snapshot algorithm to interfere with the thing it's taking a snapshot of. So these messages themselves are not included in snapshots. Questions? So yeah, so we're going to talk more about this next time, and I'm going to actually write down all the steps of the Chandy-Lamport algorithm. We don't have time to do it today. But there's a question in chat, which is the marker message sent immediately after the first event in the snapshot? So yeah, well, I don't know what you mean by the first event in the snapshot, but the way that the algorithm works is you take a snapshot of your own state, which includes all of the events that have happened on you up until now, and then you send a marker message. Somebody just asked about vector clocks. So the question is, are the vector clocks, if used, part of the snapshot? So vector clocks aren't actually part of the Chandy-Lamport algorithm. I guess they're, you could think of this as being related to vector clocks in the sense that when we get done, we're going to have a snapshot that doesn't violate happens before in these ways. So after you were done taking the snapshot, if you were to go and assign a vector clock to every event, then you would see that that you hadn't included anything in the snapshot that led to inconsistency. But vector clocks they're not explicitly part of this algorithm. In fact, this algorithm predates the invention of vector clocks. Another question in chat is, are these independent snapshots or smaller pieces of a larger snapshot? So yeah, I think I said that a second ago, but yeah, S1 and S2 here are snapshots of individual processes, and then the purpose of this algorithm is to collect individual snapshots of processes that can then be later stitched together into a global snapshot that makes sense. So next time we're going to go through a much more detailed, or actually we're going to go through this simple example again, but we're going to talk about it in more detail. And then we're going to go through a much more detailed example of the Chandy-Lamport algorithm. I'm also going to share a blog post that I wrote, which is about the Chandy-Lamport algorithm. So it turns out that there's this same example that gets reused over and over. And somebody put it in their lecture slides, and it seems to be copied by everyone. But for one thing, there's like some mistakes in it, and then it's also, in my opinion, just kind of hard to understand. So I'm going to use that same example for this for explaining this algorithm, but I'm going to try to explain it in a way that doesn't make the mistakes and is a little bit makes a little bit more sense. Last question in chat. So this is a way to flush messages in transit. Yeah. Okay. So yeah. So great point. Yeah. So when we talked about so this earlier picture I had. Not sure where it went. But the earlier picture I had where this was part of the snapshot here, and then this message from C to D got included in the snapshot as well, because this marker message came in later. So yeah, so this here would actually get included in the snapshot, even though it wouldn't be a causality violation if it wasn't. It does get included there. So I would say this. So the purpose of this snapshot algorithm is not really So when you're running the snapshot algorithm, messages that are in transit get included in these snapshots. But I wouldn't describe this algorithm as a way to flush messages in transit, because the point of this algorithm is more like looking at events that have already occurred in a system and then trying to take a snapshot of that system, which you could then use for things like debugging or checking whether a certain property of the system is true. All right, that's it for today. We're already out of time, so next time we're going to get into a lot more detail about the Chandy-Lamport algorithm. See you then.